So welcome everybody, and today we have an improvement of an algorithm for bounded the WC dimension graphs. And this will be presented by Krzysztof Potępa, but the result is joined with Lech Duraj and who?
And Filip Konieczny.
And Filip Konieczny. Okay, I think we are ready to start.
Thank you for the introduction and for the opportunity to speak. So I will talk today about diameter algorithms for graphs of bounded VC dimension. So let's start with definition of graph diameter. So in our setting, we will consider only unweighted and undirected graphs. So the simplest possible setting. Each edge has weight 1 and they are not directed. And the diameter of the graph G is distance between maximum distance between a pair of vertices in the graph. Okay. So when we talk about a diameter problem, we mean a computational problem where we want to compute this diameter in time independent of diameter size. And when we talk about K diameter problem, we have some constant K parameter, and we want to test if the diameter is at most K for a constant K. So now in this case, we allow to have dependence, polynomial dependence on parameter K, for example, even exponential. Okay, so two classical algorithms for general graphs, I'd say folklore algorithms is, the first one would be to run BFS from each vertex. We just compute single source shortest paths for each vertex separately, and it runs in V times E time. And if the graph is dense, then we can actually speed it up a bit using matrix multiplication, but this is of course impractical. And surprisingly, it is very difficult to improve upon this basic algorithm with BFS. Namely, if SETH hypothesis holds, Wasilewski-Williams and Rediti proved that there is no subquadratic diameter, even subquadratic algorithm for 2 diameter. So even in the setting when the K is 2, if we want to test if diameter is 2 or larger, there is no algorithm to do that, assuming the SETH, of course. So there are 2 directions where we can take this now. If we want to obtain a subquadratic algorithm, the first option is to consider approximation. So we sacrifice the quality of solution to get better runtime. And the other option is to consider some restricted instances of graphs and design algorithms specifically for them that run faster. So one such class that's very popular, I suppose, are graphs of bounded tree-width, where tree-width is bounded by a constant. And it has been shown that in this case, actually, we can answer K diameter in linear time if we assume that both tree-width and the parameter K are constant. We have exponential dependence here. We also have planar graphs. So if we talk about K diameter, the variant where we can have the dependence on the diameter length, then we can show that if planar graph has diameter at most K, then its tree-width is bounded by 3K, if I remember correctly. So we can just run the algorithm for tree-width and get linear algorithm to test this. But for planar graphs, we can actually do better. We can compute the diameter no matter how long it is in time subquadratic in number of vertices. And it was a breakthrough by Cabello in 2019. It was V to power 11 by 6, if I remember correctly. It was later improved to this exponent by Gabrielkowski and others. So this is the state of the planar graphs right now. Okay, and we can also consider geometric intersection graphs. And there was a paper by Brinkman and others where they proved a bunch of lower bounds and some upper bounds as well. So in this setting, it is actually a little bit different, because if we talk about graphs, intersection graphs, we can have an implicit representation, just the objects in the plane, and we can avoid dependence on edge number, right? If we have many objects in the same point on the plane, we have a clique. So if we run an algorithm that is dependent on edge count, then it is not very fast. But we can actually, in many instances, we are interested to design a subquadratic algorithm in the number of vertices if we are given such implicit representation. So first example is the unit segments intersection graph. What I mean here, we have segments of unit length. They can be rotated arbitrarily in the plane, and they are vertices of the graph. And two segments are connected by an edge if they intersect. Okay, so the standard definition. And actually, they proved that there is no subquadratic algorithm for free diameter in this case. So we don't know what about 2 diameter, but there is no subquadratic for 3 diameter, and it also rules out diameter computation, of course. Other interesting class are unit squares in the plane. So in this case, they actually proved that the diameter can be solved in linear time. So what I mean by unit squares in plane, I mean they are all axis aligned. They are all they are all rotated the same. They all are all objects in the plane are exactly the same. Okay, so we have some squares with the rotated by the same angle, and again we define graph by intersections. Okay, but if we go into higher dimensions, then actually already for 3 dimensions we cannot compute diameter in subquadratic time. And also they proved that if we have 12 dimensions, then there is no 2 diameter algorithm. So it's even stronger result, because in 3-dimensional space we don't know, maybe we can have some algorithm dependence with polynomial dependence on the diameter length, for example. And there are also 2 other natural classes. Unit balls in plane, and we don't know anything about them. We don't have upper bound and we don't have lower bound. And if we allow 1 more dimension, if we have 3 dimensions, then there is no, it's not possible to compute diameter. Okay, so now we may ask if maybe there is some common parameter that all these interesting classes share that makes them tractable. And in particular, I mean planar graphs, these unit squares in plane and unit balls in plane, because in case of unit balls, we cannot prove the upper bound. So maybe we cannot we weren't able to prove lower bound. So maybe there's an upper bound. And it turns out that these 3 classes have one common parameter, namely they have bounded distance VC dimension, which I will define now. So when I talk about hypergraph, hypergraph is a pair of vertices and some hyperedges. So hyperedges are just, each hyperedge is a subset of vertices in X. And now VC dimension of a hypergraph. To define it, we need first a definition of a shattered set. So, for example, if we have some subset of vertices Y, then we say it is shattered if we can cut each possible subset of using hyperedges of the graph. So we take each hyperedge from the hypergraph, we take its intersection with the subset of vertices Y, and we want this set to be the power. So we want all subsets of Y to be cut out. If this is the case, then the set is shattered or not shattered. And VC dimension of a graph is maximum size of shattered set. Okay, so if someone sees it for the first time, it might be quite weird. But what it actually says, this enforces some kind of structure on the graph, that we have not many possibilities how these hyperedges interact on subsets of vertices. So this is the definition of VC dimension for hypergraphs. And now to define distance VC dimension of graphs, of normal graphs, we just take the ball hypergraph. And it's the VC dimension of ball hypergraph. By ball hypergraph, I mean hypergraph where vertices are the vertices of the graph, of the original graph, and hyperedges correspond to all balls in the graph. And by ball, I mean we take a vertex V, we take some radius K, and we take all vertices in the neighborhood that are not further than K from V. And the ball hypergraph is the set of all such balls. And we define distance VC dimension of G as VC dimension of the ball hypergraph. So what this means is we have some structure on the in the graph if we talk about the neighborhoods, and this might help us with computing the diameter. So there are many classes of graphs which actually have bounded VC dimension, distance VC dimension. So one easy example are interval graphs, where you have intervals in the online, and vertices are intervals, and classically we have edge if they are intersect with each other. Such graphs have VC dimension at most 2. Also, planar graphs have VC dimension at most 4, and it is a nice, quite easy proof. We take a clique of 5 vertices, and we show that we cannot shatter all subsets of 2 vertices in the clique. We can also generalize it to KT minor free graphs, where the VC dimension is bounded by T minus 1. And also, we in our work, we proved that if we take an intersection graph of convex shapes, and I mean that each convex shape is identical. We have some one convex shape, for example, a unit square, axis aligned, and we build an intersection graph of such shapes in the plane, then VC dimension of such graph is also distance VC dimension of such graph is also bounded by at most 4, like in planar graphs. This is a very similar proof, slightly more edge cases. So, is this parameter useful? It turns out it is. Namely, a few years ago, it was proved that if a graph have distance VC dimension at most t, then we can actually solve the k diameter problem in subquadratic time. So here we have this algorithm has dependence on the diameter length, but if k is constant, then we don't care. And it's already improvement because for general graphs, we cannot solve 2 diameter, if you recall. So the exact complexity is here we have E times V, and here if we compare it with the classical simple algorithm with BFS, we have V times E. Here we have sublinear dependence on vertex count. We have slightly smaller exponent here, which is dependent on square of VC dimension. And the second thing they were able to prove, they were able to prove that if the graph is H minor free, then actually we can compute the diameter in truly subquadratic time. We can get rid of this dependence on diameter length. And this is based on this result for distance VC dimension, but they also employ sublinear separators in graphs to remove this dependence on K. And now what we did is 2 things. The first thing, we optimized and simplified the algorithm for graphs of distance VC dimension that is bounded by D. So we got this exponent down to some nice value, 1 minus 1 over D. And we believe that it might be best possible with this technique, but I'll talk about it at the end, maybe. So this is a nice exponent. I think it begs for a lower bound, which we cannot prove, but maybe someone can. And the second thing we did is we adapted these techniques to intersection graphs. Namely, we solved the problem for convex polygons in the plane. So we have a fixed convex polygon, and the graph is just intersection graph of some translations of this convex polygon. They are all rotated the same. And in this case, of course, we want to remove the dependence on number of edges, because we could just build the graph and run the first algorithm. That's pointless. We want to remove the dependence on edges because we might have large clicks, and we can do that. We get an algorithm with subquadratic complexity in number of vertices, and this exponent here comes from the fact that that this distance VC dimension for convex shapes is bounded by 4. So it's actually the same as here, but we substitute for D. Okay. So if there are any questions, feel free to interrupt me. Now we'll move on to proving stuff or results. And the overview for the remaining of this talk is as follows. We'll start with a brief summary of the algorithm by Dukov and others, this previous algorithm, because we are basing on it. Then we will show how to improve the exponent. And then we'll move to the intersection graphs. So first we will show that if there exists a certain data structure for the intersection graph, then we can compute the diameter faster. And finally, we'll show this data structure. Okay, so now we'll see how to compute the diameter in subquadratic time for graphs of bounded VC dimension. Sorry, I'm a bit sick. That's why I'm not in person today. Okay. So the main tool that we'll use are the interval representations, and it is a means of compressing the neighborhood information. So, for example, let's look at adjacency matrix of a graph. So we have vertices in some order here, and we have 1 in the cell if they're connected by the edge, and 0 if not. Okay, so if we look at a single row in such matrix, then it is the ones then denote the next one before. Okay, so this is a ball of radius 1 set at V4. And if we store this matrix explicitly, then for general graphs, of course, for example, if we store all the ones in the matrix, then if the graph is dense, if this information is somewhat dense, then we have quadratic memories, so we cannot hope for any subquadratic improvements. So idea here is to use to compress this information by taking maximal intervals. So for example, if we look at this row, we see that we have 3 adjacent ones. So instead of keeping these 3 ones separately, we just keep interval from 4 to 6. Okay. And here we can just keep 2 intervals for the V4. And in general, if we do this for each vertex, we get the interval representation of this matrix. So for each vertex, the ball is encoded by some maximal segments of vertices that are inside this ball. So I told you that this is adjacency matrix, but we can also consider K-adjacency matrix if we talk about, if we want to encode information about balls of size K, of radius K, then we can do the same thing. And of course, for general graphs, it doesn't work. For example, if we take a random graph if we take a random graph, then the number of intervals will be linear for each vertex. And the question is if we can actually, maybe we can permute vertices somehow to bring down the number of intervals in each row. So it turns out that this is exactly what VC dimension gives us. Namely, if the graph has VC dimension bounded by a constant d, then we can find a vertex order for each k. We can find a vertex order pi, such that maximal number of intervals that represent some k-ball is sublinear. Okay. So what this theorem says, we actually can compress the whole neighborhood information. If we have k adjacency matrix, we can compute this whole compress this whole information into subquadratic memory by appropriately permuting vertices and keeping the interval representation. And actually, we can compute a good vertex order pi in polynomial time. Okay, so we can compute such vertex order that is sublinear, but unfortunately, this polynomial is not subquadratic, and we want to use this technique somehow in to solve the diameter problem in subquadratic time. So we need an algorithm that works in subquadratic time. So what authors of this previous paper did, they designed an approximation algorithm which actually runs in subquadratic time and computes a worst order, a worst vertex order, but still the number of intervals is sublinear. But we sacrifice the exponent here, and this epsilon d is actually d squared times some constant. So that's where their complexity comes from. So here we make this sacrifice. Okay, so now we have this main tool. In our toolbox, we can order vertices such that we can compress the neighborhood information. And what's the idea behind the diameter algorithm now? We want to use dynamic programming. We will compute interval representations of all R balls in the order of increasing R. So we start with a trivial representation. We have balls of size 0, so each vertex is just a single vertex. Then we can have arbitrary vertex order for such case, and each interval representation is just a single element. And the important question is how to grow these neighborhoods. So we have, suppose we have this encoding of R balls. So we have this vertex order and interval representation, and we want to take each ball and grow it by 1, increase its size by 1. And how to do that efficiently? We want to operate on the input is in compressed form, the interval representation, and we want to output it as well in the compressed form. We want to do it in the subquadratic complexity. So there are 3 steps. The first step is obviously to compute the new vertex order, because we need to have separate vertex order for each R for it to work in the good complexity. So we start by computing this new vertex order for the R+1 using the algorithm for the previous slide, which works in subquadratic time, but it just gives us vertex order, not the balls encoding. The second step is to take these representations for R balls, compute, grow them by 1, but still with respect to this old vertex order. And finally, we make a translation to the new vertex orders so that we maintain linear size. So the first step is just running the previous lemma. So let's see how the second step is done. So we have the encoding of R neighborhoods. We want to grow it by 1. And we want to do this with respect to this old vertex order. So we want to compute interval representation of r+1 balls, but with respect to vertex order for r balls. So the key observation is, very easy observation is, if we want to compute balls that are larger by 1, then we can just sum balls of all the neighbors. So if you have vertex x, you have a vertex, and vertex x have some neighbors. Here we just take these for each of these vertices. We just take the ball of size r, and also including the ball of vertex x, and we take their sum. Okay, and then we get, we can get a ball of size r+1. So of course, if we do this, if we do this directly, then it's not subquadratic. We cannot do this on the vertex subsets. We need to operate on interval representations, but this is easy. We just need to sum these interval representations. So we have some sets of intervals, and we just want to compute a union of all these interval representations, and it can be easily done with a sweep line in good complexity. And what's the complexity of this step? So for each vertex v, we take all interval representations of its neighbors, and we compute their union in time relative to their this interval's length. So the complexity here is, if we sum it, we have that each interval representation of each vertex is used degree times, and since each interval representation is sublinear, if we sum it over all vertices, we get that it's E times V2, so something sublinear from V. Okay. So if there are any questions, feel free to ask me. I don't know if the pace is okay or I'm going too fast. All right. So now we have these representations. We have some interval representations of these r+1 balls, but they are with respect to all the vertex order, and we don't have guarantee that that these interval representations will be sublinear in V. In particular, they can be big. They can be as big as the runtime here. So we need to convert it to the new vertex order that we computed for r+1. To maintain the property that the encoding is subquadratic. So this is the tricky part. So what we actually have, we have this interval representation for R balls here with respect to some vertex permutation, and we want to convert it to the new permutation of vertices. So we just want to permute the columns of this matrix, and we want to compute interval representation in this new matrix, right? We want to permute the vertices and compute the representation with the with respect to this new permutation. So it is not clear how to do this. For example, if we take a row here for V3 and we want to compute the representation for V3, it is not clear how to do this separately for each row. And the idea is that we will compute for each column here. We compute set of vertices for which intervals end on this vertical line. So, for example, here we want to compute set of all vertices. For example, if we have V4, it is 0 in this column and 1 in this column. So this is a place where interval starts. So we want to find this. We want to compute a set where V4 is inside. And if we have V3 here, then it is not this position is not end of an interval, so we don't want to output it. So what we actually want to do, okay, if we compute for each such vertical line set of rows where the change happens from 1 to 0, then we can recover the interval representation easily from it. So how to compute this for a single column here? We just need to find a symmetric difference between these two adjacent columns. And since the graph is undirected, this matrix is symmetric, the columns are the same as rows. So what we actually just need to do is take symmetric difference between V1 and V5 in this alt representation. Okay. So to summarize here, for each such vertical line, we take symmetric difference between two of the rows in the alt representation, and then we can from this recover the intervals. And the key is that if we have two interval representation, then we can quickly list all places where they differ. Okay. So the time complexity of such procedure is actually output sensitive. For each vertex V, we need to scan each alt interval representation, and the complexity is dependent on the output size, so on the new interval representation that we produce. And since these vertex orders are nice, we have sublinear complexity in terms of V. So that's pretty much it. If we talk about the basic algorithm for general graphs of bounded distance with dimension, the key is to grow these neighborhoods one by one. And if we want to test if diameter is at most k, we just need to check if the computed k balls contain all vertices. Because if diameter is larger than k, then we have some two vertices that are further than k apart. So if we take a ball centered at one of these endpoints of diameter, then it cannot cover all vertices. Otherwise, the diameter is at most k. So this gives us an algorithm, and that is sublinear in V. No, and we have this body exponent from this approximation algorithm for vertex orders. Okay. So are there any questions so far? Okay. If not, then we'll continue. So now we're moving to our work. We have all the things we need. We'll show how to improve this this exponent of V. So what's the bottleneck of the previous algorithm? We know that there is a nice order where this exponent is 1 minus 1 over d. But the problem is that we don't know how to compute it in subquadratic time, so we cannot use it. And what they did, as I said, they just they sacrifice the exponent. They show an approximation algorithm that computes a slightly worse order, but still subquadratic. And that's the that's the reason why they get this worse exponent. So what we can do about this? We can, of course, try to design an algorithm that is subquadratic and computes a vertex order with such nice exponent, but we don't know how to do this as well. So instead, we will weaken the condition that we require from these vertex orders, namely, let's assign a weight wx to each vertex x. And now we require only a weighted sum to be nice. So instead of requiring each individual vertex to have sublinear interval representation, we just want the sum over all vertices to be sublinear in V. Okay. So what we have here, we have a sum over sizes of interval representations times the weight. we can assign a weight to each vertex, and we want sublinear times sum of weights. So clearly, if we have a vertex order that satisfies the maximum, then it satisfies this weaker condition as well. And it is actually it would be the only vertex order that satisfies this condition for all possible choices of weights. We, on the other hand, only want this to hold for this single choice of weights for vertices. And it turns out it is enough. So if we look again at the diameter algorithm, the time complexity of a single step of computing r+1 balls from r balls, we can write it like this. We have dependence on the sizes of these interval representations, and we want this sum to be nice. So each interval representation is used to degree times. For r balls, and for r+1 balls, it is used just one time. So actually, if we have algorithm like this, where where for each interval representation we know how many times it will be used in the future, then we can always set weights appropriately. In this case, we want to set them to degree of a vertex +1. And if we do that, then we find a vertex order that satisfies the bound for these weights, then we just get a good time complexity, and we get a nice algorithm that works in with better exponent. Of course, if we can find a path with such weights, and it turns out we can. Okay, so the key contribution here is a simple algorithm that in subquadratic time computes this good vertex order for arbitrarily chosen vertex weights. Okay, and it's not an error here. It actually is faster if the distance VC dimension of a graph is larger, then the algorithm is faster, and it is because we need to win a vertex order which will be worse, and we can do less iterations of the algorithm. So for standard situations where this VC dimension is 4, like for planar graphs, this is very fast. It is faster than it is definitely subquadratic, and we can use it. Okay. So now, so the algorithm is extremely simple. Actually, it is certainly not obvious why it works. So I will start by showing the algorithm because it's very nice, I think. And the proof that it produces a good vertex order is quite technical, and I'll just show you hand wavy proof sketch for the case where all the weights are equal to 1. So we have unweighted variant of this. Okay, so how the algorithm works. We start by sampling t vertices, S1 to St, from the vertex set. And we want the t to be v to power 1 over e. Okay, so this is where this part of complexity actually comes from. We want to sample a subset of vertices of such size. And we want to pick, we want to assign probabilities to each vertex that it is picked, which are proportional to their weights. So probability that v is picked is its weight divided by sum of all weights. Yeah? It's proportional to its weight. Okay, and when we have this subset of vertices, they can it can be multi-set. We don't care if we sample the same vertex again. It doesn't really matter. We now do the following. We start with a single bug V with all vertices. And we take the first sampled vertex S1, and we divide this bug into 2 bugs. The first bug are vertices that are in the k ball of S1. They're not further than k from S1. And the other bug are the rest vertices that are further. Okay, so we just take this ball centered at S1 and we cut this bug of vertices V into two parts. And we place these bugs next to each other. So in general, we will have a sequence of bugs of vertices. Now we have two bugs. Let's say it is V1, 1 and V2, 1. So now we take the second vertex, second terminal, let's say, S2, and we do the same. For each bug, we cut it into two parts using the ball centered at S2. And it might be the case that sometimes one of these bugs is empty, then we ignore it. So for example, here we have a case that V21 is contained within the ball centered at S2 and it was not cut into parts. So we have just one bug. And we continue to do so with the next terminals. And when we process all the T terminals, all these T randomly sampled vertices, we are left with some sequence of vertex bugs. And we claim that we can, in each bug, we can order vertices arbitrarily. We can take concatenation, and that is a good vertex order. Okay. So we have a vertex order. In each bug, we can order arbitrarily, and we just concatenate these bugs. They are the order of bugs is dependent on this procedure of splitting. Okay, and we claim that this vertex order is nice. That we get such bound for size of interval representations for this vertex order. Okay, so it looks like magic probably. So why does it work? Okay, so I will just show, as I said, I will just show a rough sketch of proof for the case where the weights are 1. So the unweighted case. So in this case, we just want the sum of interval representations for this vertex order to be subquadratic in V, namely 2 minus 1 over D. Sorry. Okay. Or in other words, we want the average interval representation size to be sublinear, not the maximum, but the average. Okay. So it turns out that instead of, if you look at the sum of intervals of interval representation, we can instead count number of differences between adjacent balls. So if we have two vertices that are adjacent in the vertex order, we take the k balls centered at them, we take the symmetric difference, and we count how many differences we have. So the number of interval ends by self-duality here is roughly equal up to the constant to total of differences between balls centered at adjacent vertices in this vertex order. And we have two key lemmas here. The first lemma is allows us to bound number of groups that are formed by the algorithm, and the second lemma allows us to bound differences between vertices that are in a single group. Okay, so the first lemma says that if we do this procedure for some vertex set S, this splitting procedure, then we can have at most S to the power of D bugs, and it is actually a reformulation of Sauer-Scheller lemma for hypergraphs of bounded VCT dimension, so it holds for general hypergraphs, and this S doesn't need to be random for it. And the second lemma comes from epsilon nets, and it says that if we have two vertices in the same bug, so they have the same same image on S, we have small difference. Namely, if we sampled 1 over epsilon vertices to do this splitting procedure, then difference between balls in the same bag can be at most epsilon v. Okay, so if we look at this hierarchy, how we did splitting, the first lemma says that we can have the first lemma just bounds the number of groups on jth level. For each level, we have bound for the number of groups, and the second lemma bounds this on each level. If we look at a bag that was formed on this level, we have a bound for the differences in this bag. And if we consider the worst case scenario is that we have the bags are split as soon as possible, because I said that when we take the next vertex and the splitting, some bags might be not split. The worst case is that we split them as much as possible as soon as possible, because the differences are the highest then. And so we can say that on each level we have j to power d minus 1 new splits if we do that. And maybe we'll not go into this equation exactly, but if we sum it over these two things, then we actually get the good bound. Okay, that this is sublinear and actually subquadratic, and the sum is subquadratic, and is 2 minus 1 over d actually. Okay, so that's the rough idea why it works. These two lemmas, one is for the VC dimension that is sparse, and the second one is that the random subsets for epsilon nets. Okay, so to summarize this part, we have an algorithm that computes such vertex order, and of course we can the sketch I have shown is for the unweighted version, but the weighted version works as well, and it turns out that it works just the way we want. Yeah. So now if we take this key and we plug it into the previous algorithm for diameter, then we improve the exponent. Okay. So are there any questions to this? Okay. If not, then we have the first part behind us. And now what we want to do, we want to adapt this algorithm for implicit graphs. By implicit graphs, I mean graphs, for example, geometric intersection graphs, where we don't have explicitly given all the edge set. We have, for example, in case of geometric graphs, we have objects in the plane, and the edges are defined implicitly based on these objects. That we have an edge if there is an intersection. Sorry. Okay, so for example, if we look at this at unit square intersection graph, this will be our main focus here. So we have unit squares on the plane. We have edge between them if they intersect. So we can prove that that this unit square intersection graph actually have bounded distance VC dimension by 4, just like planar graphs. So if it is sparse, if we don't have many edges here, then we could just build the graph explicitly, compute all the edges explicitly, and run the previous algorithm. And when we get some algorithm, it will be subquadratic if the edge count is not much. But of course, we can have these large clicks, like here. We can have many overlaying unit squares, and it generates a lot of edges. So we would like to design an algorithm that doesn't depend on edge count. Okay, so to do that, we need some data structure to operate on subsets of vertices here. At least this is our idea. So we show that for unit square intersection graphs, we have a data structure that persistently maintains subsets of vertices and allows two operations. The first operation is add neighbors, and it is simple. We have a subset of vertices, subset of squares in the plane because of unit squares. And we want to add, we are given some vertex V, and we want to add to the set all neighbors of V. So V, the whole closed neighborhood of V. Okay. So in case of unit squares, we are given some square, and we want to add to the set all squares that intersect with this with this given square. And we want to do it persistently. So if we have this representation, this data structure representation for a vertex set S, then we don't want to destroy it, to return a new representative from the data structure that represents this new set extended by this neighborhood of V. And the second operation is these differences. So we are given two vertex subsets, two representatives in the data structure of these vertex subsets, and we want to quickly list all vertices that are in the symmetric difference of them. So all vertices that are only in one of these sets. Okay, so we'll use this exactly to compute this this compressed encoding quickly. Okay, the first operation we want to work in worst case constant time. I mean by O with tilde, I mean of course that we hide logarithmic factors, so it is actually log n. And least differences operation we want it to work in output sensitive time, so its time is dependent only on this output size, on number of these indices in the symmetric difference. So we actually show that such data structure is possible not only for unit squares, but also for convex polygon intersection graphs. So it's the case where we have a fixed convex polygon with constant number of sides, and we have intersection graphs of its copies in the plane. And now we'll show that that if we have such data structure and the graph has bounded VC dimension, then we can actually compute diameter in subquadratic time without dependence on edge count. So in particular, for convex polygon intersection graphs or for unit squares, we have for constant diameter k, we have v to power 7/4, where this comes exactly for the VC dimension 4. Okay, so the plan now is to assume that this data structure exists. We'll come back to it at the end. And I'll show how to adapt the algorithm to use this data structure. So first thing, we will use a different encoding now. In the previous algorithm, we used the interval encoding. So for each ball was encoded by maximal disjoint intervals. And we had this vertex order that guarantees that it is sublinear. But we also said that instead, if we look at differences between consecutive balls, so if we take two balls centered at vertices that are adjacent in this vertex order, then the average symmetric difference between these two balls is small, is sublinear. So instead of using these interval representations, where we for each vertex we store the ball as intervals, and now we store for each we have some order on the balls of the graph, and we store symmetric differences between consecutive balls. So if we look at this matrix visualization here, interval representation is for the rows, where we have for each row we have these intervals, and this dual encoding that we'll use now is for columns. Each column here is of course the ball as well, because it's symmetric mass, and we store for each pair of adjacent columns, each pair of adjacent balls, we just store the differences. So For example, here we just store a set with a single vertex v3. So if that wasn't clear, we have a formal definition here, how the encoding works. So again, we have this, we have vertex order for, if we compute our neighborhoods, we have vertex order for our neighborhoods, our balls. And we have a set of vertex subsets, d1 to dn, which is a delta encoding of these R balls. So precisely what this means, if we take the ith ball in this vertex order, then its R neighborhood, R ball, is the symmetric difference of a prefix of these sets D. Okay, so we have a set of symmetric differences, and the ball is just symmetric difference of the prefix. Or in other words, each set di for the first ball is just this ball, and for I larger than 1, we have difference between adjacent balls in this order. And again, the same vertex order that worked for intervals works here. Yeah, we can just press algorithm and we get the vertex order that satisfies this equation, that the average size of set di is sublinear. So in total they are subquadratic. Okay, and if we run this algorithm directly, this time complexity came from the fact that we need to compute this. When we run this algorithm, we sample vertices and we need to compute balls centered at these vertices, and we use a shortest path algorithm for this, BFS. So that's where the edge dependence, edge count dependence come from in this general algorithm. But if we talk about geometric graphs, for example, unit squares, we can easily simulate the BF in time independent of edge count, and we get an algorithm that is truly subquadratic in vertex count, not edges. So it is okay. We can compute these vertex orders in good subquadratic time. Okay, so how the algorithm works? We follow the same principle. We start with a trivial neighborhood, 0 neighborhoods. So each vertex is just a single vertex. There's nothing more. And we want to grow these neighborhoods, these balls, by 1 in each iteration. So we clearly have dependence on diameter size. So the question is, how do we go from R balls to R plus 1 balls? How do we grow the neighborhood by 1? Okay, so we again start by computing this new vertex order using the previous lemma. Then we change a bit. So previously we just computed directly these interval representations. Now we have this delta encoding, and what we want to do, we want to build representations of these new growth balls by 1 in the data structure. And once we have representations of these all balls, we just want to output their encoding, the delta encoding. So the second step, we are given delta encoding of R balls, and we want to build R plus 1 balls in the data structure, and that's where this data structure operation add neighbors comes from. We want to add the whole neighborhood, and turns out that the second step can be done quickly. We'll show how it works in a second. And once we have these representations built in the data structure, we can just use this find differences operation, which lists differences between two sets in the data structure to compute new delta encoding. Okay, so the first interesting step, actually the most interesting step, is this second one. How do we build these representations? So here we use a slightly different method than before. Before we had a vertex, for example, X. In the general algorithm, we took the balls in each of the each direct neighbor of X, and we summed over it. Here we do different. Here we do something different. We have this vertex X. We have this large R ball centered at X. And what we do, we take each vertex that is inside, and we its neighborhood, and we sum them over. So if we do this, this whole ball will grow by 1. So formally, we have the observation is that we can just sum the direct neighborhoods over all vertices of the R ball, and we get the R+1 ball, of course. So now let's think how to do this with this data structure. So the naive way would be to build each R ball independently, separately, and we can just use this add neighbors operation, because add neighbors does exactly this. We have a set of vertices. We are given a vertex X, and we want to add the whole neighborhood of X. So if we run add neighbors for each vertex X in the R ball, we get the representation of R+1 ball. But of course, we cannot do that because this set can be large. We cannot do it. We want to have an algorithm that takes the delta encoding of these neighborhoods, and based in time complexity only dependent on that of this delta encoding. We want to build all representations at once. So the fast way to do this is to use divide and conquer. And I'm not going to go maybe into details how it works exactly. So this talk doesn't take 2 hours because I want to show the data structure also. But the rough idea is we have a recursive procedure that takes the delta encoding and takes some representation in the data structure that initially is empty, and once we proceed recursively, we'll add some vertices to it. And the observation is that if we have a vertex V that is only present in the first set D1 and not in the other sets of the delta encoding, then this set V will be then this vertex V is in all balls encoded by this delta encoding. So we can instantly take all such vertices V that are only present in the set D1 and add them to S. Okay, and once we do that, we just cut this. We just cut the encoding in half, and we run proceed recursively on both sides. But in the set D1, we remove the vertices that we added already, and we pass down this set, so this representation S. And it turns out it's enough. If we do this optimization, that adds vertices that are in D1. So the key idea here is that once this procedure, this divide and conquer procedure finishes, we have these representations data structure, and they actually share some common parts between them. So that's where these optimizations comes from. And we can prove that the whole thing works in time dependent only on size of total size of the delta encoding and number of these sets. We just get an additional logarithmic factor from the divide and conquer procedure. So that's a rough idea how the second step works. Are there any questions to this? I don't want to prove this exactly, just a rough idea. Okay. If not, then the third step is to compute the delta encoding from these representations, and it is simple. We have built all these R+1 balls in the data structure, and to extract delta encoding, we can just use this second operation of the data structure that lists differences. We can just directly compute using this operation each of the sets di by listing differences. So it is simple here. And since find differences is output sensitive, the complexity of this step would be dependent only the size of output. And the size of output is subquadratic because we have a nice vertex on it. Okay, so to summarize this this part, this whole I call it lifting procedure, where we take R ball to R plus 1 ball, use this data structure to compute the data delta encoding, and the same as before. If we want to test the diameter is at most k, we want to check if for each vertex v, the k neighborhood covers all vertices, and in terms of delta encoding, it means that we just need to test if the first set contains all vertices and all other are empty. This means that all are equal to v, so it is also simple. And if we can do this data structure, which I didn't show how to do yet, then we get a nice subquadratic algorithm here with a clean exponent. Okay, are there any questions here? Okay, so if not, the last part is how to design data structure that does this thing. And I just show few figures, without going into details, because technical details are, it's quite nice. I think it's not very involved implementation actually, but we'll just go high level. Okay, so we'll show it for the unit squares, because I said that we can generalize it to arbitrary convex polygons, but this is just technical and not very interesting. We just focus on unit squares. It's simple. Okay, so suppose we have this unit square intersection graph, and we have this red square here. We want to run this add neighbors operation, and what it does, we want to add to the set of vertices. We want to add all squares that intersect with this red square. Okay, so the key thing is that all these squares have the same size, so we can actually think of it differently. We can instead think that all other squares points, we shrink them to a single point, and we grow the red square by 2. Okay, so the squares that intersect this red square are actually squares whose centers, these points which are the centers, lie in a square that is twice larger. So geometric interpretation of what we want to do in the data structure is we want to persistently maintain some sorry. Okay, first we have some static set of points, that is the input for initialization, and then we want to persistently maintain subsets of points, marked points from this set, and the marking operations, the add neighbors, is actually operation where we just have a big square, a unit square, and we want to add all points that are inside, mark all of them. And find differences is, of course, operations where we have two versions of the data structure, of the persistent data structure. We want to list all points that are different between them, which are marked in one and not in the other. Okay, so the idea is that we'll compute a hash we'll compute a hash of marked points, and more precisely, not only for the whole set, but we'll have some division of the plane into parts, and for each part we'll store a hash of these of marked points that are inside in a tree data structure. And if we have hashes of marked points, then we can easily implement the find differences method. If we have in a tree structure, we can just compare hashes and descend down if they are different. So the first thing, suppose we have these points in the plane. The first thing we do, we split the plane into stripes, where each stripe has height has a unit height. So why do we do that? Why do we do this split? If we do this, we can notice that any unit square, no matter where it lies, can intersect at most two stripes. It can either lie like this, and it intersects these two stripes. With the upper one, for the upper one, it comes from the bottom, and for the lower one, it comes from the top here. Other possibility is that it sits like this, exactly in a single stripe, but it doesn't matter, because if it covers single stripe, it's even easier than two. So the idea is that once we do that division of the plane into stripes, we can handle each stripe separately. Okay, so for each stripe separately, we'll compute hash of marked points. And now each mark operation that was a square originally is an operation where we have some rectangle where this is 1 and this is some height h, and we want to mark all points that are within such a rectangle, and it comes either from the top or from the bottom. Okay, so how to handle a single stripe here? So the idea is that now we will build a segment 3 over the x coordinate. So we have all the points inside the stripe. We sort them by x coordinate, and we'll build a segment 3. And the segment 3 will store. So, for example, if we have some base interval in the segment 3 that handles this part, it will store, of course, the hash of marked points inside. Okay, and we can define something called the lower border. So if we take all the squares that came from that intersect the bottom border, they form some kind of border here from the bottom, and all the points that are below it are marked. And the same we can do for the squares that intersect the upper border. So this is shown in red. And okay, and for example, if you want to compute hash of all covered points here, we cannot count this point twice, because we might have a situation where there's a square that intersects the upper boundary, have a square that intersects the lower boundary, and they intersect each other. There might be a point that is below two borders. Yes, it's below the blue border, and it's above the red border. So actually these borders may interact between each other, and these points that are common for them, they need to be counted once in the hash. Okay, so it's not like we cannot handle them separately. We cannot have one data structure that computes hash of covered points by the red border, and for the blue, we need to handle them together to take account of such points. Okay, so let's think. Let's quickly think. What's the idea? What's the idea here? How to update it? How to update the hashes? So, if a new square comes, which intersects the lower boundary of the stripe, if this rectangle that we have here lies entirely below the blue border, then we don't need to do anything. It doesn't cover anything new, right? This whole fragment was already covered by the blue border, so we don't need to update hash. And we can easily detect such situation if we store appropriate things in the nodes of the data structure. Another easy case is if the square lies like this. So if this upper segment of the square lies entirely above the border, it's also simple. We don't have intersection with the blue border or the red border. It turns out we can also maintain enough information in nodes to add hashes of these points, of these newly covered points here. Okay. So the hard situation is when the newly added square intersects the blue border or the red border in some points. For example, if it likes like this, then in this part, it doesn't cover anything new. So we don't want to update hash with points here. But in this part, it covers this. So if there are any points here, we want to update hash accordingly. And the idea is that okay, so this situation is hard, and also other hard situation would be if it intersects also the red border. It can lie like this, for example, right? Many cases, but the key insight is that each new square, if we add a new square here, it can intersect each border, blue and red, at most 2 points. And why is that the case? It's because this border is formed by unit squares. So if we look at let's look at, for example, any interval here that has unit length 1. Then if we look at the set of all squares that intersected the bottom boundary, then it can either lie like this, where it intersects also the left border, or lie like this, where it intersects the right border. So in each such square, if we look at this blue border, it is weakly bitonic. It first decreases, then increases. Okay. So if we add a new square, it can only, for example, at this height, it can only intersect it at 2 points here and here. And the same holds for the upper border. So in total, whenever we add a new square, it intersects the red and blue border at most 4 times. So what we can do, we can actually, this operation, we can actually split the square into 4 parts and handle it separately, because each operation of adding a square is actually an interval operation here, and we can just split it into at most 4 parts somehow and handle each separately, and each case is easy. So for example, the part of the square lies entirely below boundary or entirely above the boundary. Yeah, so that's it. We have at most 2 intersections with each boundary, so at most 4. And it is enough if we reduce it to these easy cases. For example, if we have some base interval here in the segment tree, we just need to store the maximum and minimum coordinate for each of these borders. We also need to store hash of points covered by blue border, by red border, and by both borders. And this is enough to update everything in a good time. So that's the idea behind data structure. Okay. So that's it. That's it. So if we build this data structure, if we apply it to, if we combine it with the previous algorithm, we have some quadratic algorithm for unit squares and also convex polygons if we generalize it. And now some final remarks. Okay, so here I just have a recap what we did. So the first algorithm was for the general graphs of 1 VC dimension. Here our key contribution is this algorithm that computes vertex orders with weights. And if we apply it to this previous algorithm, we get a better exponent here. The second main contribution is extending the approach for convex polygon intersection graphs, and the key thing here is the data structure and also the algorithm divide and conquer that allows to apply it to this case. and we get a nice subquadratic complexity here. Of course, it's still dependent on the diameter size k, but it's still an improvement because, for example, for unit squares, it was known that 2 diameter can be solved. We can tell apart diameter of size 2 from diameter of size 3 or larger, but it was unknown what to do with larger k. We can do it for arbitrary constant k. And of course, the natural direction where we can take this is try to remove this dependence on k. So this brings me to the open questions. Perhaps the most interesting thing is what to do about unit disks, because we don't have for the intersection graph of unit disks in plane, we don't have lower bound, we don't have any lower bound, and we don't have any algorithm, even for the case of 2 diameter. So can we use our approach with data structure to solve unit disk? We would need to design a similar data structure for the unit disk intersection graphs. And this is much harder because if we use a similar approach that like for the squares, we heavily use the fact that there are not many intersections. As I said, if we have this upper and lower boundary, we have at most 4 intersections. For disks, we can have arbitrarily many. So we cannot adapt this approach directly. We can have many unbounded number of intersections between disks when we add a new disk. Yeah, but also, of course, these graphs, disk intersection graphs, of course, they have bounded VC dimensions by 4 because these are convex shapes. So that explains why it's hard to get lower bound for the complexity, I believe, because all these lower bound proofs, they actually they are actually adaptation of the proof for general graphs, for which somehow encode the construction in these geometric intersection graphs. And these examples, they definitely don't have bounded VC dimension. So for these cases where we had that higher dimensions, we don't have bounded VC dimension, and we can actually build these graphs. In this case, we don't know how to do that. So I think that's also interesting. It might be hard to get lower bound for unit disks as well, if it is not possible to get a faster algorithm. Okay, the second thing is complexity of diameter for graphs of geometric intersection graphs. So what I mean here, complexity of computing the diameter, right? We don't want to, can we get rid of the dependence on diameter length? So, and compute arbitrarily long diameters in subquadratic time. So the first thing is for geometric intersection graphs, it might be easier than for the general case, because we have some kind of separators here, clique separators that we maybe can use here as an analog for the separators in minor free graphs. The first question is actually about general graphs of bounded distance VC dimension, because we have this testing algorithm for k diameter when it is constant, but we don't know if we can compute diameter if it is long in subquadratic time. It is unknown if we can do that. So maybe actually it is possible for all graphs of bounded distance VC dimension. We don't know about that. And the last thing is lower bounds, because as I said, our algorithm has this exponent 1 minus 1 over d. And actually, it seems to be the best possible if we use an approach that encodes these neighborhoods using vertex orders, because for general hypergraphs it can be proved that if they have that there exist hypergraphs of VC dimension d such that we cannot find an order on vertices which has better exponent than this. So for this algorithm, if algorithm uses such encoding, then we cannot improve upon this encoding anymore, okay? So maybe, just maybe, it's a lower bound because it looks nice. I would hope it is lower bound, but we have no idea how to attack this. And but maybe it is. Okay, so I think that's all. Thank you very much for listening, and I'm open to your questions now.